Okay, so in a previous video when we looked at a dynamic implementation of the binomial model and I used Espen-Haug's VBA code, I took these parameters based again on Brody the temple, and at 5,000 steps when I executed that, the estimation took about 2 seconds or so, so that's coming in from previous video clip. So with 5,000 steps, those parameters, we're getting the 9.0657, and it's taking about 2.6 seconds. Come out of there and look again. Well, it's about the same, 2.3 as opposed to 2.6 seconds or so. So it's obviously faster than static implementation of the binomial tree. One other additional, in this video I'm going to address how to speed up by truncating the zeros. If we go back to a very basic Cox-Ross-Rubinstein tree, we initially had these parameter values for Cox-Ross-Rubinstein, and this is a 15-step tree. Generally speaking, as we change the values here in our binomial construction, there is a series of zeros in the binomial tree, and they take a fairly predictable pattern. Truncating, having the ability to truncate the zeros out of your binomial tree reduces the number of estimations you've got to make by maybe as much as a third of overall number of nodes. And if we have an efficient algorithm to trace back, to take these values and do backward recursion with basically these values as opposed to the entire set of option values. Again, keep in mind when we set up this tree is based on the stock prices, and if we multiplied by U and so on, or D and D, we generate these values. So combinations of U and D multiplied by the original stock price generates the tree. And then underneath we have initially the intrinsic values, and then in the preceding nodes we have the time values of the options, and in this instance it is the American option. Okay, some of our estimations though are basically wasteful. If we go back into our dynamic tree, dynamic binomial based on Espen-Haug's construction, not the static tree, we can see that when we're working out the value of the option in the backward recursion, we start at I equal to 0 going up to I equal to j at each successive set of each array of nodes. In other words, if we take a look at the backward recursion process, normally we estimate these values, the intrinsic values, then we implement the backward recursion and so on. But a large number of these nodes, particularly in this section here, they are zero values, and they have no material effect here. So if we have a zero value here and here, the fact that we have a zero here, the fact that we have zero here is not influencing at all. So that's finding a way to leave out zeros, or truncating the zeros, will speed up estimation time significantly. So okay, we want to do that, and we want to figure out a way of going from Espen-Haug's relatively straightforward construction, kind of parsimonious type construction, very, very efficient, to truncating the zeros. Now, to do that, we managed to reconfigure the Espin-Hoag's tree, and Qianru Shang set out a few nice little techniques where we invoked pot call parity based on MacDonald and Schroeder, and there are some pot call parity conditions that link the value of an American pot to the value of an American call, and that's something I'll look at in a moment. But I used that. Qianru wrote the code here, and she also developed additional code in terms of defining where the truncation occurred in the Cox-Ross-Rubinstein tree. So she managed to identify, well, first of all, identify where the last zero occurs in terms of the binomial. So if we go back in, take a look at the binomial, take a look at just for in this instance here, take a look at where the last zero occurs in terms of, that's a put, let's look at a call, where the last zero occurs in terms of the parameter values that we have here, for instance. Okay, so again, we have the stock price tree, binomial tree. Underneath we have the backward recursion, and then we try to define where in the ultimate array the first non-zero value occurs. And if we use this formula, the formula set out, we define it as num. It is the integer of the log, natural log of k, divided by s multiplied by the power of d to the power of s by d to the power of n, divided by the natural logarithm of the ratio of u divided by d. Again, we can estimate that using this formula. Again, it's a similar type formula, and we find that value, if we didn't have integer, of course it's the value is 8.8. When we put integer here in Excel, we go to the whole value, and it's the lower value. So if you like, as we can see here, 8 represents the last zero in terms of only in terms of the call option, because the construction changes dramatically with a put option, as you might observe. But for the call option, we can say there's a kind of a pattern here where we can define a num 8, where in the ultimate column the value of the last zero is at where I is equal to 8. So the i's run up here 0, 1, 2, 3, 4, 5 up to 15, and the last zero value occurs here at 8. Okay, now that's useful because it means if we want to know where to start in terms of backward recursion, and we want to exclude the zeros from the pentultimate array, pentultimate column, then we take num and we subtract 1 away. And okay, so we go back to our code and we take a look. Now, the way that was managed, again, Qianru adopted the process here, and she defined a start. The start basically just means, instead of starting at 0, instead of defining, in the usual way, we define j as being, as in the backward recursion, as going from the pentultimate column, n minus 1, and then adjusting by 1 for each preceding column. But I then is defined in terms of not I from 0. Before, in the, if you look here in the backward recursion, I started at 0 and then I went up to j. If we want to exclude the zeros, we don't start with I equal to 0. In fact, we start with I equal to start. And start is obtained by getting that num, which in the Excel was 8, and we subtract away n minus 1 minus j, which in this instance j is equal to n minus 1 for at least the first value. So in the ultimate column n, the number here would be equal to 8. But as we go through the loop and j increases, the num is brought down until such time that the value of that when we get to 6 here, so when we get to this value here, we no longer want to start other than at a value of I equal to 0. So Qianru developed a little algorithm here that ensures that we don't start with a negative value for I. It's truncated also at 0, or there's a floor value of start with 0. It never becomes minus. Now that's quite useful. So in the code that we have here then, it's basically the same, it's very similar. We've to Espen Hogue, we've got rid of the Z's, which were a feature of Espen's code. We've just truncated, and we've also invoked MacDonald and Schroeder put call parity conditions when we want to run the value of the put. But if we run the value of the call here, again, we want to make sure, okay, we take the value here of 5,000 steps. For, as noted before, when we ran 5,000 steps in the Espen Hogue style code, that took of the order of 2.5 seconds. Again, there's latency here because the values, parameter values go up to the server and have to return. So 2.39 seconds to get this value here of 90657, and we're doing 5,000 steps. When we truncate the zeros, we should see some improvement here in terms of speed. Let's take a look at that. Okay, so we run again, it's for a call option, and it's American 5,000 steps, and again the values are values based on the Brody to Temple 1996. And again, we recover the same value, but the number of steps, okay, is now down close to 2. Let's change our value here to P. So for a put option, just to verify that the put call parity condition set out by MacDonald and Schroeder actually works. Okay, so we run for the put. This is again the truncated for the zeros, and we will run here for the put in the Espen Hogue type style code. So inverted commas and P, and remove this value here, and let's run. And we can see back here with the Espen Hogue style code 17.7237. And we come back then into our code here, 17.7237, that's fine. For the put option, it's taking 2.4 seconds where we've truncated the zeros. And where we've used Espen Hogue's type, actually, so for Espen Hogue style code, it is, okay, so dynamic binomial based on Espen Hogue, running 5,000 steps, estimating an American put, it's 2.4 seconds. When we truncate the zeros with 5,000 steps, same parameter values, it's taking less than 2 seconds. So we're getting a speed improvement. And that also means we can drive up the 15,000 steps if we run here and run here. We can increase our level of accuracy as well. And just to demonstrate, we run both of these together. And the nice thing about this online compiler is that we can run a number of estimations simultaneously, and it doesn't, it's not taxing on our own processor. Okay, so I'm going to pause for a second for those values to come up. And we can see here, using again by truncating the zeros, right, we're getting some efficiency in terms of estimation time. It's now down to 20 seconds, well, 20 seconds for 15,000, and for Espen Hogue style code at 15,000, the put is estimating 23 seconds. So we reduce the estimation time by 15 seconds, and we get the same result if we compare.